about the in the discussion of audio coding, we will be paying our attention on the MPEG-1 codec, and especially we will cover the polyphase filter bank implementation. So, this is MPEG-1 coding part. This is what we are going to discuss. Now, in the last class, when we were talking about the AC3 decoders, and then we happened to talk about the analysis and synthesis filters for the multi-channel or multi-band filtering, that is what we were talking. And there we had seen that there are two basic aspects towards the implementation of such multi-band filters. One of the ways is that we implement an FIR filter in the time domain, but there we happen to add their frequency domain characteristics. Okay. So, some kind of an overlap and add techniques we have to adopt in the frequency domain, and we apply a frequency domain alias cancellation. Okay. That is one of the approaches, and the second approach is to first window the samples, and after that we are going to talk about the that is followed by the time domain alias cancellation approach, whereby we take the transforms of the windowed samples, and then we consider the filtering in the transform domain, and we had seen that this is what we apply in the AC3 audio codec, and the same thing is also applied to the MPEG-1 audio coding also. Okay. Just excuse me for a minute. So, we will first start with the MPEG-1 audio coding basics. So, there what we do is that the basic flow diagram that is followed in the MPEG-1 audio coding goes like this. We have a filter bank first, and this filter is realized in the form of a multi-band filtering, and in multi-band filtering we apply the same technique, that means to say the time domain alias cancellation, and we adopt a frequency domain filtering rather than the time domain filtering. So, this filter bank implementation we will be discussing very shortly. Now, once it is filtered, actually it is filtered into 32 different subbands, right. So, these 32 subbands would correspond to 32 different critical bands, okay, based on the perceptual audio, and then we will be having for each of these 32 filter banks we keep one first in first out kind of buffer. So, these are the FIFO buffers, and we have FIFO buffers for each one of the samples. For each of the subbands. Okay. So, there are 32 such FIFOs, and each FIFO is 12 sample deep. So, these are 12 samples. So, this can store up to 12 samples. So, that because there are 32 such subbands and we have 12 samples per subband. So, we have totally 32 into 12, that means to say 384 samples, they form one audio frame in MPEG-1. Okay. Now, all these FIFO outputs, okay, these 12 samples together, they are accumulated in the form of a buffer. So, this buffer, the frame buffer will have a total capacity of 384 samples. So, we have 12 from the subband number 0, 12 from subband number 1 and etcetera up to 12 from subband number 31. So, this is FIFO number 31, this is FIFO number 0, this is FIFO number 1 and it is storing 12 samples. So, now this frame buffer, this contains the 12 subband data, I mean 12 points for each of the subbands, okay, 12 samples for each of the subbands. Now, what we can do is to find out that amongst this data, whichever is having the highest value, okay, based on that we need to do some scaling on the data, so as to have the maximum usage of the dynamic range of the samples. So, the frame buffer is put through a scale factor. So, there will be different scale factors for different subbands. So, we have a scale factor buffer, okay, which will store the scale factor values, or where the scaling factors will be decided based on the sample values what we have in the frame buffer, based on the maximum value of the sample, and the scaled values, okay, will be stored in a buffer, okay, where the quantization will be applied. So, the quantization will be applied on this scaled value of samples. Okay. So, what we have is that from this scale factor buffer, okay, these 32 subband samples whatever we are getting, okay, this will get quantized. So, this is for the subband 0, subband 1 up to subband 32. So, there will be quantizer. So, the quantizer will be chosen based on what? Based on the psychoacoustic consideration. Okay. So, we have a psychoacoustic model and beat allocator. So, psychoacoustic model, as you know, that this works on the masking characteristics. So, psychoacoustic model plus beat allocation, and the scaled sample values are quantized through this quantizer, and then the quantized samples are put for encoding. So, here we obtain the encoded subband samples. For all the 32 subbands. So, this is the flow diagram. So, I could not draw in one page. Okay. This was the first page. So, we start with the filter bank, then the frame buffer, then the scaling is applied, and after scaling the samples are quantized. The quantization is decided by the psychoacoustic model and beat allocation, and then we have the encoded subband samples. So, this is the flow diagram for encoding a frame of audio data. In fact, this form of encoding is the simplest form of encoding. In fact, MPEG 1 standard that specifies 3 layers of encoding, and these are the layer 1 encoding, which is the simplest, okay, then followed by layer 2, and the last one is the layer 3, which is the most complicated one. Although in terms of the compression efficiency, layer 3 will be the best, okay, but for not so but for applications where we do not require that much of I mean compression efficiency, their layer 1 implementation happens to be the simplest. In fact, there are two psychoacoustic models which are defined. The simplest is the psychoacoustic model 1, which I mean the layer 1 and the layer 2 is based on the psychoacoustic model 1, whereas the layer 3 uses psychoacoustic model 2, which is a more complicated psychoacoustic model. Now, in layer 1 we find that a frame is composed of 384 samples, whereas in the case of layer 2 a frame is composed of 1152 samples. So, there what we have is that this FIFO buffers in the case of layer 1 is only 12 samples deep, and there we have 36 samples for every subband. So, 36 subband means that we have 36 into 32, which means to say 1152 total samples we have, and this 1152 samples, this 36 samples per subband, they are again divided into 3 blocks, okay, of 12 samples each. So, each block will function like a layer 1 encoding, and in fact the scaling factor can be applied differently for each one of these blocks. Okay. So, for each 12 samples we can apply a different scaling factors. Now, one thing which you can see, that the scaling factors need not be the same for all the subbands. We are not applying uniform scaling factors to all the subbands, rather the scaling factors are different for different subbands. Okay. So, now we come to the implementation of this filter bank, and as I have already told you that instead of going in for an FIR filtering approach in the time domain and then doing the alias cancellation in frequency, we adopt a windowing followed by the DCT, which in this case happens to be the modified discrete cosine transform, the MDCT, and then we have the alias cancellation in the time domain by adopting the overlap and add technique, which we had already discussed in the previous class, right. So, let us come to the filter bank implementation. Yes, any questions?
So, in this encoder, the output of this filter banks, won't they be going to a FFT estimator block?
These are already coming. See, these filters are already I mean the samples that we obtain through the subband filters. So, they are already the filter bank outputs. Okay. So, they have been already MDCT'd, okay, right. So, I mean actually in MPEG audio coding standard, okay, one thing which I think that I mentioned a couple of classes back, where I was showing the generalized block diagram of perceptual audio coding, where I had mentioned that the PCM samples that we obtain, that goes through two different paths. One path is where we compute the FFTs, okay, and the idea of calculating the FFTs there was to obtain the tonal components, okay, based on which the psychoacoustic model acts and there the beat allocation is decided. The another part is the direct encoding path. Now, we are talking in this case about the direct encoding path, and in order to encode, what we do is that we adopt this kind of a filtering approach, whereby we are I mean applying the windowing followed by the MDCT, okay, and the reversal will be done at the decoder. Now, we are talking only up to the encoding part over here. So, now we will be talking about the filter bank implementation, that how we implement the filter bank. Now, before we do that, okay, let us go into some theory behind the polyphase filter. So, we will talk about the theory of polyphase filters. And why we call it polyphase? See, it is because basically this approach is first proposed by Rothweiler, okay, and in Rothweiler's approach, a multi-phase filter implementation has been analytically established. It is shown that if you are having a prototype low pass filter, okay, then you can realize a bank of filter by simply modulating that filter. What you have to do is to multiply the filter transfer function, okay, or I mean if you are considering the filter in the z domain, what you have to do is to modulate that, okay, by the center frequency of the band pass filter. And if you have a bank of band pass filter, okay, to be implemented, then you can simply multiply by that band pass filter center frequency and you can realize a bank of filter like that. Okay. So, this was Rothweiler's approach, and this approach we will be making use of, and we will be showing that how this approach basically translates to the same way of implementing a windowing function followed by the DCT. Okay. So, we will show that. So, what we have to do is to have a bank of band pass filter. Okay. Let us say that we are showing a bank of band pass filters, okay, whose responses are like this. Okay. So, here we have the amplitude and here we have the frequency. Okay. And now, what we do is that we first start with a low pass filter. Okay. So, it is a low pass filter, okay, which is followed by a band pass filter, and then we will be having bank of band pass filters that goes like this. So, we assume that the sampling frequency is unity. So, assume the sampling frequency, or rather Fs you can write, okay. Fs is assumed to be 1 hertz. Okay. So, that the frequency to be covered is 0 to, if it is 1 hertz, then what is the maximum angular frequency that you are talking of? That is to be, I mean 2 pi divided by 2, that means to say pi. Pi will be the maximum frequency. In fact, 2 pi radians per second will be your sampling frequency. So, that the maximum frequency that you are talking of is pi. Okay. And you are assuming that there are bank of M filters to be synthesized. Okay. So, bank of M filters to be synthesized. So, what is the nominal bandwidth for each of the filter? The nominal bandwidth for each of the filter is going to be pi by m. So, the nominal bandwidth is going to be pi by m, okay, and the filter center frequencies are odd multiples of 2 pi by m, pi by 2 m. Okay. So, in that case, this center frequency what we are talking of, okay, this is going to be pi by m, okay. Then this is going to be 3 pi by m, okay, and this is pi, and the bandwidth is going to be pi by m. So, here to here we have pi by m, or if you are taking from here to here, that is pi by m. Huh? Pi by 2m, yes, pi by 2m and 3 pi by 2m, sorry, yes, yes, correct. Center frequency is pi by 2m and 3 pi by 2m, right. As we have already written down that the nominal bandwidth is pi by m and these are odd multiples of pi by 2m. So, that we have pi by 2m, 3 pi by 2m, 5 pi by 2m and so on. Okay. Now, the band pass filters, the I mean the prototype low pass filter, we assume that it is an FIR filter, okay, with impulse response h of n. So, the prototype low pass filter we assume that it is an FIR filter with impulse response h n. And its Z transform is h of z. Now, the band pass filters, okay, they are composed of two complex filters which are FIZ and GIZ. These are the two complex filters that exist at where? At the positive and the negative frequencies. Okay. So, all real band pass filters. So, we should say that all real band pass filters so this is composed of, I mean is composed of two complex filters, right, is composed of two complex filters FIZ and GIZ. FIZ's center frequency are all located in the positive frequencies and GIZ's center frequencies are all located at the negative frequencies, right. So, at the two complex filters that exist at the positive and the negative center frequencies. So, what we have to do is that we can express the FIZ and GIZ as follows. So, FIZ, in fact, the suffix I stands for the ith filter, okay, the ith band pass filter we are talking of. So, FIZ will be given as h of z being the transfer function of the, I mean is the z domain transfer function of the low pass prototype, okay. But in this case Fi of z will be not h of z, but it will be the complex exponential involving the center frequency. So, it will be, I mean because the center frequencies are all odd multiples of pi by 2 m. So, that is why f I will be e to the power minus j to j pi into 2 I plus 1, okay, divided by 2 m, okay, this into z. So, if you are substituting I to be equal to 0, in that case what you get 2 I plus 1 to be equal to 1. So, it is minus j pi by 2 m. So, this is the first center frequency, okay. So, the first center frequency is located at pi by 2 m, okay. So, f of 0 you obtain by simply multiplying by e to the power minus j pi by 2 m z, okay. So, that realizes the f 0 z component, and the G0z component, or in general the Giz component, will be written as h of e to the power j 2 pi, not the minus sign, because this refers to the negative center frequencies. So, that is why it will be written as e to the power j 2 pi 2 I plus 1 by 2 m z. So, that together this f I z and g I z, okay, that realizes the real filter. Okay. So, we can number this equation. So, let us say that this is equation number 1 for us and this is equation number 2. So, equation number 1 and 2, what we have derived is the complex filters in z domain, what we have obtained by multiplying the h of z, multiplying z by the exponential of this e to the power minus j pi 2 I plus 1 by m. Okay. And we get a band of filters, okay, using 1 and 2, we get a band of filters for I is equal to 0, 1 up to m minus 1. So, we get m such different filters, right, and we can in fact obtain the overall filter response h I of z as what? We can have some constants, we use constants a I, b I, c I and d I, whereby we can express this overall transfer function h I of z as a I f I z, okay, plus b I g I z. Okay. And likewise we can apply the, I mean we can have, so this is the analysis transfer function h I of z, okay, the combined analysis function, and then we can also express the corresponding synthesis filter k I z as c I f I z plus d I g I z, okay, where a I, b I, c I and d I are complex constants. Okay. Now, h I of z forms the analysis filter bank for I is equal to 0, 1 up to m minus 1, and k I z forms the synthesis filter bank. So, this is the synthesis filter bank and this is the analysis filter bank. So, pictorially we can show like this, okay. I mean this realization, let us say that this is equation number 3 and this is equation number 4, okay. Pictorially we can show like this, that this is the input, okay. It is put through m different filters, okay, consisting of m different band pass filters consisting of H0z, okay, H1z up to HMZ. And because each of these bands happen to have 1 upon m times the original bandwidth, okay, there are m different filters, okay. So, the total frequency range is pi, and each of them, as I have already shown you, that each of them covers only pi by m as the bandwidth, right. So, each filter bank has a bandwidth of pi by m. So, we need not have to use the sampling frequency, the original sampling frequency, rather we have to decimate and decimate the frequency, the sampling frequency by a factor of m. So, there will be a decimation by a factor of m, downsampling. So, downsampling by m, that we have to do for all these filter banks, okay, and then it goes into the digital channel. Okay. So, these are, so this is the encoder part, or rather the analysis part. Okay. So, this is the analysis filter bank, and correspondingly in the synthesis filter bank or the synthesis realization, what we have to do, just the reversal. So, we have upsampling by m. So, that we have to do for all these filter banks, there should be an upsampler by a factor of m, and this should be followed by the K0, the corresponding synthesis filter bank. So, here we should have a filter K0Z, here K1Z, and the last one will be, oh, this should be m minus 1. Okay, you did not point out this mistake to me. So, this is H m minus 1 and this is K m minus 1 Z. And now, what we have to do in order to compute the output, in order to obtain the output, we have to combine the responses of all these synthesis filters. So, there should be a summer, okay, where we are going to combine the outputs of all these synthesis filters, and here we will be obtaining the output. So, the output will be obtained over here. So, this is the output of the filter. Okay. So, this is the synthesis filter bank. So, this output should be exactly equal to the input if it is a perfect reconstruction. Okay. So, if the H0 and Z0 are so chosen that or rather the HIs and the KIs are so chosen that the output becomes equal to input, in that case, that is the condition for perfect reconstruction. Okay. Now, if in this equation, okay, what we have written as the linear combination, I mean HIZ, the analysis filter and the synthesis filter written as the linear combination of this FIZ and GIZ. Okay. If there we impose a condition that AI is the complex conjugate of BI. Okay. AI, BI, CI, DI all are complex constants, I already mentioned. So, if we choose AI to be equal to BI star, okay, in that case the impulse response of HI, what we obtain, the impulse response of HI, this happens to be real, okay, and it is given by, so if this is so, the impulse response of HI is real, and is given by HI of n equal to the real part of AI into cosine. I mean this comes through a simple manipulation. Okay. Just what you have to do is to break up the complex exponential term into the sine and cosine and impose the restriction that AI is equal to BI star, okay, whereby you will be finding that the imaginary parts they cancel out, and what you will be obtaining is real part of AI times cosine pi 2i plus 1 into 2n plus 1 divided by 4m. Okay. So, this is the HI of n. So, we are getting the, so we are now trying to have the HI of n, which is nothing but the impulse response of the band pass filter HI what we are realizing. Okay. This is the real part of it. Okay. So, this is out of the I mean multiplication with the real part of AI we get this. Okay. This minus I the imaginary part of AI that has to be multiplied by the sine of pi 2i plus 1 2n plus 1 divided by 4m. Okay. They are the not only the square bracket ends, but also the curly bracket ends. Okay. And this multiplied by h of n. Remember what is h of n? H of n is the prototype low pass filter response. Okay. So, now just try to interpret this equation. Okay, equation number 5. Okay. You interpret. Okay. I mean before you interpret this, let us have one more relationship mentioned. Okay. Very simply, if you are going to use h I of n to be the impulse response of the filter, okay, the ith bank filter. Okay. In that case, what will be the response of that filter? It will be given by the convolution of the input samples. So, now if you are denoting the input samples as x of n. So, the input samples are given by x of n, where n is equal to 0, 1 etc. Okay. And supposing we have the length of the filter tap to be equal to. So, L is the length of the filter tap, and we are realizing an FIR filter, then the filter output for the bank I. So, the filter output of bank I, this will be given by SLI, that will be equal to the summation n equal to 0 to L minus 1 x L minus n into h I of n. Simply by the convolution we will be obtaining this. So, this is equation number 6. Okay. That is to say, the filter output obtained as a convolution of the ith band pass filters impulse response and the input samples. Now, if in equation number 6 you substitute equation number 5, okay, then what you get? Instead of h I of n, you write this expression. This expression has got two parts. One is this cosine and the sine part, and this is getting multiplied by h of n. And if you substitute over here, then what you are getting, this x, or rather to say you are getting x L minus n, that gets multiplied by the cosine terms, the sine terms, and then you are also getting an overall multiplication by h of n, right. That overall multiplication by h of n, that remains. Now, what is that overall multiplication by h of n? Okay. If you realize the overall multiplication by h of n, okay, using a windowing function, okay, windowing is also a kind of convolution. So, now if you are implementing that using windowing, then what remains to be tackled is x of L minus n, or rather the input samples, okay, that multiplied by the cosine terms, or that multiplied by the sine terms. Okay. Now, this cosine terms, whenever you are multiplying the samples by the cosine terms, what you are essentially doing is the obtaining the DCT. When you are multiplying by the sine terms, what you are doing is the DST, you are doing the discrete sine transform. Okay. Now, basically whenever you are substituting equation 5 in equation 6, you are obtaining the DCT or DST of the input samples, that multiplied by the prototype low pass filters response, prototype low pass filters impulse response, okay, and this prototype low pass filter that serves basically as the windowing of the time domain samples. Okay. So, we can just write down this statement that substituting equation 5 in 6, we obtain the DCT or the DST of the input samples multiplied by the prototype low pass filters impulse response, that is H of n. And we can also make a statement that the latter serves as the windowing of time domain samples. Now, what we can do is that after substituting equation 5 in 6 instead of writing the big equation, okay, let us show the block diagram of the implementation. So, what we do is that one of the efficient implementation that we can talk of, you see that here we are talking of the bank i's implementation. Okay. Now, there are m such banks. Okay. So, how to obtain this m banks? So, what we have to do is that we can consider that the total length of the buffer, okay, we consider an input buffer, okay, where we have the input buffer is of length L, okay, and we have the samples coming in, okay, and then we have the sample indexes as I. So, we have here 2m samples, okay, gathered, okay. The next 2m samples, okay, are gathered in this part of the buffer, the next 2m samples are gathered in this type in this buffer, and the last, so that we index the samples in the second bank as 2m plus I, okay. We index the samples in the third part of the buffer as 4m plus I, because up to here we already have 4m samples. So, the last one will be 2 small m capital M, okay, into 2 small m capital M plus I. So, this is going to be the index of the samples in the last buffer, and then what we are doing is that we have to multiply this by the h of n. Okay. So, to do the multiplication by h of n, okay, any doubts or difficulties? 2 lm, yes, not m, yes, right, 2 lm plus I, please do the correction, I made a mistake. And then we have the multiplication by the windowing function. So, this basically indicate the multiplication by the windowing function, and then we are summing them up. So, there is a summer block, okay, and then the summed output is stored in a buffer of 2m words, and then we apply the sine and the cosine transforms on this, and in fact applying the sine and the cosine transform together is nothing but applying the MDCT. Okay. So, this is the sine cosine transform block, and there with 2m words as input, okay, with 2m samples as input designated as 0 to 2m minus 1, we will be obtaining m sample output, okay, from the sine cosine transform block or the MDCT block. So, this is 0 1 up to m minus 1. Okay. So, these samples are the frequency domain samples, what we are obtaining by windowing and sine cosine transform. So, the same thing, I mean what we had written down, okay, in form of the equation, okay, this is just an implementation of this, and because this implementation basically involves modulating the center frequency of the filter, okay, by a factor of, I mean by an amount of pi by 2m, okay, or the odd multiples of pi by 2m. Okay. So, that is how it realizes a polyphase filter. Okay. You are taking the low pass filter as the basis, the prototype low pass filter as the basis, okay, and then by multiplying it with the complex exponentials of the center frequencies, okay, you are obtaining the different filter banks through a polyphase filter technique. Okay. And in fact, the MPEG audios, okay, filtering, what I had mentioned in the first place, okay, remember that we started with this diagram. So, this filter bank in MPEG 1 is realized in a polyphase manner, okay, which is very similar to this. I mean this is a generalized way of representing, but specifically the MPEG 1 audio's polyphase filter implementation, okay, that goes like this. Okay. Please follow this. So, in the MPEG audio what we have is that we take an input of 32 samples, 32 samples, these are in the time domain. Okay. Now, these 32 samples, they will go into where? They will be going into buffers, okay, and the buffer, as you are seeing over here, that the buffer is partitioned, being partitioned into all the subspaces corresponding to the different filters, right. So, we now have this 32 samples that goes into what we refer to as the X FIFO. Okay. So, here we have the first 32 samples, here we have the earlier 32 samples, here we have the earlier block of 32 samples. Like this we have got 16 previous blocks of 32 samples. So, this buffer is of size 512 samples, this buffer stores up to 512 samples. So, that we have got 16 blocks of such 32 samples. Okay. So, the idea is that whenever 32 samples arrive, okay, this is in the form of a shift register arrangement. That is to say that the current 32 samples will be stored over here, the earlier block of 32 samples will move to the next cell, the 32 samples which were there in this cell move to the next, and so on. Okay. So, totally we are storing 512 such samples. Okay. And on this 512 samples, or rather this is 0 to 511, because we have 512 samples. So, now this X FIFO outputs, okay, this will be multiplied by the windowing function, okay, and this is called as the analysis window, right. So, this will be multiplied by the analysis window, and the analysis window is referred to as the C window. So, C window is nothing but the analysis window, and the windowed outputs, they are buffered, as I mentioned that they are added and then buffered. So, what we do is that this windowed outputs, okay, they are collected, okay, in a buffer which we call as the Z vector. Now, what is the basic idea? The basic idea will be that we are feeding 32 samples at the input, and we should also have 32 subband samples at the output. Now, to get 32 samples, that means to say that if I want to make my capital M to be equal to 32, then at the input of the MDCT, how many samples I have to feed? I have to feed 64 samples, okay, 2m number of such samples. So, I have to feed 64 samples, and we have to then buffer, okay, in a buffer space of 64 samples. So, what we do is that this z vector, okay, we partition into 8 such blocks of 64. So, 0 to 63 and so on up to 511. So, it is partitioned into 8 such blocks. Okay. So, what we do is that this z vector outputs, okay, consisting of 0 to 63, okay, the next block will be 64 to 127, okay, and so on, and the last one, the last block will be coming from here, okay, this block of 62. So, you can calculate this, this will be 428, okay, is it 428 or 448? 448. So, 448 to 511 will be here, and they all will be summed up together, and there we have the summed vector as the y vector. Okay. So, y vector will be consisting of 64 elements, 0 to 63. So, all these filter banks, okay, so all these individual z vector components are added. Okay. So, basically it is a realization of this and this together. Okay. So, now this buffer of 2m words, what we have is nothing but this y vector. So, this y vector is fed to the, so this y vector of 64 samples okay, that is fed to the DCT DST block, or rather the MDCT block, okay, and this realizes the 32 subband samples 0 to 31. So, these are the subband samples. So, for every 32 input time domain samples that you are feeding over here, you are getting 32 subband samples as the output from this bank. Okay. So, that your sampling in this case is a, so this is a critically sampled system. Okay. For every 32 inputs we are getting 32 outputs. Okay. And this is the polyphase filter implementation. So, what you can see essentially in this implementation again is that we are first passing it through an analysis filter, and then the I mean we are first passing it through a windowing. The windowing is followed by addition, and the addition is followed by performing the MDCT, and then in the transform domain we are obtaining 32 subband samples. Okay. And this 32 subband samples is what you are going to feed into this first in first out. So, 0 to 31. So, these filter bank outputs will be stored in FIFO. So, all the first set of 31 samples will be stored in the first cell of this FIFO. So, when the very first 32 samples arrive, they will fill up this block of the FIFO, or rather to say the first in first out. So, the last parts will be filled up, okay. And then when the next block of 32 samples arrive, the next part of the FIFO will be filled up. So, that when 12 such set of samples, okay, are obtained for each one of the subbands, okay, then on this we can do the further processing, because in that case we will be obtaining 32 into 12, that is 384 samples, which forms an audio frame, okay. And on 384 samples we then apply I mean put it to the frame buffer, perform the scaling, perform the quantization, and it is not only the encoded samples, but also the bit allocation information, the quantization information, the scale factor information, all these have to be put into the channel. So, those who are interested, okay, to get a more detailed insight about the MPEG 1 audio standard may please refer to this paper. This is by S. Schlien, Seymour Schlien, and the title of the paper is Guide to MPEG 1 audio standard. The paper appeared in IEEE Transactions on Broadcasting, volume 40, number 4, December 1994. The page numbers are 206 up to 218. Okay. So, if you refer to this paper, you will get sufficient details. So, this completes our discussions on the audio coding and audio transmission. Okay. And from the next lecture, we will talk about the voice over internet protocol, the VoIP. So, that will be the next chapter that we take up from the next lecture. Thank you.